Okay, so time to get started. So we're going to go through section 5.6 here actually pretty fast because these are just applications, and we're just going to be using ideas of calculus that we've already developed. So I'm hoping this will blow through quickly. So the book spends a little time starting off with defining the average value of a function. The first thing we need to start with is this idea of a weighted average. So some of y'all may have seen weighted averages with just discrete finite number of numbers. And it's a pretty straightforward idea. Here's me averaging 6 numbers. Right, and I'm going to rewrite this denominator as a sum of a bunch of ones, and then I'm going to kind of group together like so. Excuse me. And what you notice is that it's this sort of considering the number of times that they're written down as what we call a weight. Right, is therefore kind of an easy way to write in a sort of a compact version of what the formula otherwise would be. Right, so this idea of weights is really just sort of a convenience. Right? Okay, so we generalize this formula like so. This is a weighted average of a list of the numbers, the V numbers using the weights, right? These numbers here are, well, it's the number of times that the numbers that we're actually averaging, how many times do they actually show up? Okay, so same basic idea. Just to give you a numerical example, and this example is actually relevant to this course. The way we're going to do averaging of exam grades and that sort of thing is a weighted average. Okay? Now the weights that I'm advertising here are not quite exactly the same as what we have for this class, right? We only have 3 midterm exams, but then there's the final exam, which is worth 30%, and then there's this whole business about homework and attendance count for add up to 10% total. So anyway, but this is reasonably close, and so anyway, let's see how a weighted average breaks down. If I can get my eraser to work, there we go. So I'm just going to write down this formula, but we're going to be averaging the numbers that we're going to average are the grades you see here, right? That's what we're averaging. The weights, given right there. So these weights are 20, 20, 20, and 40. And plug and chug, and there's your average, and it's a little, I don't mean you specifically, right? There's the average for this student, for Bob's average, is a little under 3. Okay. Everybody good? All right. Okay. So we can do the same kind of thing to find the average value of a function, which is really what our goal is here. And the average value of a function is a weighted average. It's just a weighted average. It's just that you use the size in the domain as the weights. So we're going to use the dx's basically as weights. So we're going to look at all the different values of the function. Well, not all, but we're going to look at samples of values of the function all over the entire domain, and the dx, the size of the piece of the domain that one value is representing, the size dx is the weights. So as a result, now I'm going to zoom out so we can see how this, what we've got here is really just kind of an adaptation of that. We're using, for the weights, we're using the dx's. And instead of adding discretely, we're integrating continuously. Okay, so that's the motivation. And of course, you can rewrite this a little bit. In particular, this sum of the weights, well, if the weights are the sizes, what we're talking about then is the total size of the domain, and that's an easy calculation. That's just b minus a. No problem. So that's kind of the simpler version to for computational purposes, you might take this as an easy to remember straight to the computation version of the formula. But that said, it's easier to connect, it's easier to make sense out of from this point of view, right? It's literally a weighted average and sizes are the weights. Okay. Okay, so an easy example. If you, oh yes, question.
So that example is the same one that we would use from like single variable calculus, right?
Yeah. Sometimes this is covered in single variable.
So that's not like the generic formula for R.
Correct. No, so I'm.
R1 to R1.
Yeah, that's right. So this is an example. Yeah, this is the single variable version of the general statement that we're addressing now. That's right. Absolutely. Yep.
Would you know to explain again why it's a weighted average?
Well, so I mean, the idea of weights is just kind of terminology and shorthand, right? But here's how you average numbers. Right? I mean, that's ancient history, right? But so the idea of a weight is I look at the 4 and the 4 and I say, look, it's the same number. It's there. I mean, it is 4, right? I'm viewing the 4 as being there twice, and it's just kind of the recognition that viewing the 4 there twice can be viewed as this right here.
So when we have just a two-dimensional graph, we basically add up all the area and then like average it out by dividing by the domain. But
Well,
how would we divide by a two-dimensional domain?
Yeah. No, we'll get to that in a second. Yeah. Haven't done it yet. Okay, so yeah, so still momentarily in the example where we're looking at a single variable version, then yeah, you just divide by the length. And for example, if you're looking at one arc, come on, eraser, one arc of a sine wave, right? What's the average value on one arc of a sine wave? Well, so b minus a is pi. And so it's just the integral divided by pi, easy integral, and so we get 2 over pi. Okay. All right, so to your question, if you have a 2-variable function, in other words, a 2-dimensional domain, same concept. The average value of the function, we're just averaging by the sizes of the pieces of the domain. It's just that now size, how big is a little piece of a domain? If it's a 2-dimensional domain, well, how big it is its area. So we're weighting by dA. Still a weighted average. And again, it's very convenient to notice that this denominator is, well, in this case, it's area, total area of the total domain. Okay, so again, example, if I want to look at this function x squared on the unit disk, well, on the unit disk, sometimes x squared is bigger, sometimes it's smaller, right? And varies. But on average, there's the function I want to take the average of, and do the integral, divide by the area. Of course, now on the unit disk, the area is pi. And double integral to be computed, and blah blah blah. Y'all can go through those details, but anyway, it ends up being 4th. And good to make sure that you can fill in those blanks. Is everybody happy? Okay, so why are we talking about the average value of a function? There's various circumstances where it can come up, but one immediate example of where we would want to care about the average value is this thing called center of mass. So the way you define the center of mass of a mass or a collection of masses is as a weighted average. It's literally the weighted average of position, where you use the masses themselves as the weights. Right? So which seems natural, by the way, right? So 2-dimensional example, if you have a certain amount of mass here at a point x1 and another mass m2 at the point x2, how would where's the balance point if I wanted to put my finger underneath the x-axis there and have it balance, right? This center of mass, well, those masses are the weights, and we're doing a weighted average of position. So we're going to take the x coordinates themselves, do a weighted average using the masses as the weights, and that gives us our center of mass. So that's a nice point of view on center of mass. There's different points of view you can take, by the way. The book that we use for Math 212 to define center of mass takes a different point of view. Pros, cons, but better for physical intuition, arguably. The center of mass is the balance point. It's, as I was saying before, that's where you put your finger so that it balances. And another way to say that it balances is that the amount of torque pulling on the left side, downward on the left side because of that mass, and the amount of torque, of course, pulling the other way by the, in this case, bigger mass at a shorter distance on the other side, we need the total to be zero. In other words, we need the magnitudes of these two torques to be the same. So that's just a little confirmation that y'all can do. And I encourage you to take a minute and confirm that this point has that property, that it makes the torques on either side balance. Okay, so this is the formula for center of mass if you have two masses. But you see, it's weighted average. It's the same concept of weighted average that we used in previous examples. And so if you have, instead of two single masses, if you have a distribution of mass, weighted average, right? Weighted average of position. Here now, if the mass is distributed over an area or possibly over a solid, position then is a vector, right? Still weighting by the masses. You get this formula here. And again, very conveniently, the denominator is just the total mass. Very easy. And you've got an integral left, of course, to be computed. Now, this integral, I guess technically we haven't written down the formula for an integral of a vector, but this vector, it just has a bunch of coordinates, and you just integrate those coordinates one at a time. It's kind of like differentiating a vector. You take the derivatives of a vector one at a time, one coordinate at a time. So same here. So this integral right here has coordinates that are the integrals of x's individual coordinates. Okay, let's see an example. So I've got a domain here that's the upper half disk. So this is a two-dimensional region here. And we're going to say that the density is constant, just to keep the algebra convenient here for the first time through. And this is a disk of radius a, like that. Where are the what are the coordinates of the centroid? This term, center of mass, sometimes called centroid. So yeah, where's the center of mass? Well, we have formulas from above, and the x coordinate of the center of mass is the weighted average of the x coordinates. The y coordinate of the center of mass is the weighted average of the y coordinates. Straight from the formulas. And then it's just a question of how you compute these integrals. Right, and so I'm going to go quickly through how to compute these integrals, because how to compute these integrals is techniques that we've already talked about before, right? So we get lucky with this one. If you look at this integral here, you think carefully about that integral, you'll notice pretty quickly that there's a line of symmetry there. That's a line of symmetry for the domain, and the integrand x is odd over that line. And this integral is equal to 0 by symmetry. And I remind you, you do have to provide the details on an exam. I'm leaving that then as an exercise for, voluntary exercise for y'all to do here to fill in those blanks. Make sure you can do that. It's very, very handy to be able to cite symmetry to compute that integral, as opposed to cranking out, brute force, directly. No such luck, unfortunately, with the y-coordinate of the centroid. Right, and so this is one of those landmines that we talked about last time. That just because you see a lot of symmetry, it doesn't mean that the symmetry argument is going to work. This function, yeah, that function has odd symmetry over different line, but not over the sole line of symmetry of the domain. So both of these are symmetric, but in different ways. There is no symmetry argument here, and not only can you not argue this integral to be 0 by symmetry, it isn't even 0. This integral, if you crank it out, and we're going to talk about how to do that in a second, not 0. So if you say 0 by symmetry, it's way, way wrong. I hope everybody sees the danger there. Again, I'm a huge fan of symmetry. Just don't step on the landmines. Yes?
How is X 0 by symmetry?
Well, yeah, so you've got to write down, there's several steps to be done there, right? We can talk about them in office hours if you'd like, but so you've got to write down, identify this is the line of symmetry. Then you've got to write down the formula for the reflection, right? So what does it mean if you have a point X comma Y, where does it reflect to? And then you've got to plug that reflection into the function that I'm claiming has odd symmetry.
Wouldn't all the area on the left need to be under the curve though?
I'm sorry, what?
Wouldn't the area on the left need to be under the curve?
So keep in mind, this is not a graph, right? We're looking at just the domain here. So this idea of, integrals are, negative when the area is under the x-axis, that's for graphs.
Okay.
So again, dangerous thing. So I'll flash you back to chapter 2, was it 1, 2, somewhere along in there where we were, it's a very easy mistake to make, but yeah, very important to distinguish the context. Yeah. Yeah. Is that cool?
Yeah.
Okay. Yes.
I'm not sure where this is implied, but where did you use the density?
Oh, well, the density is 1, and I guess what I should have written down here is dm. When I write dm like that, dm is density times dA, and with density being 1. Right. So this equation here just says mass is equal to density times area. In other words, mass is mass per unit area times area. So yeah, does that make sense?
Thank you.
Yeah, no worries. Okie dokie. So yeah, so here's our integral. Now, how are we going to compute this integral? Again, no symmetry argument, landmine. But we can use iterated integrals, and of course we have 2 options. Now, as y'all know, sometimes one of those choices is better than the other. And how do you know? Well, I gave y'all 2 sort of like very loose guides, right? You can try to think in terms of with this domain defined by certain curves. Is it natural to think of one of the variables as a function of the other? Maybe, kind of, sort of, but in both ways you're going to get some square roots, right? So the algebra is not particularly easier one way or the other in that sense. And what about corners? Are we going to slice through corners in either direction? Not really. Right. So there's a point of view that says our general rules, our general guidance for how to decide which way to slice does not advise us here. And so I just want to point out, and this is really kind of flashing back to earlier in chapter 5, sometimes it's good to write them both down and then kind of eyeball and look for, guidance as to which one looks nicer. And I tell you what I notice here. And I advise you all to be on the lookout for this kind of thing. I'm looking at this, the y dy, and I'm thinking, what, the very first thing that's going to happen is I'm going to get a y squared to show up, and that squared is going to kill this square root, and no more square roots. And that's awesome. So I think much better to do this one, and less better to do that one. And then, not that you can't do, this you can compute that integral. It's just much more work. Okay. New thing I want to talk about, our sort of last application. It's this thing called moment of inertia. It takes a little bit of effort to motivate why we would define moment of inertia to be what it is. And I think it's useful to know where that comes from, even though this is physics. But it's good to know where things come from, but also the way that we're going to motivate this idea of moment of inertia is through computing an integral, a very easily motivatable integral. And developing integrals is something that we're in the business of doing. That is, what we're here for. So I think this is a good discussion. Let's talk about particles rotating around an axis. Right, you got some axis, you have some particle rotating in a circle around it. Okay. And I think y'all know from geometry class from way back when that S is equal to R theta. In other words, the arc length along that circular curve is the radius times the angle. I hope that's something y'all recall. And then just take a derivative of both sides. And of course, distance per unit time is speed. The left side is easy. Distance per unit time, right? Speed, which I'm writing here as the magnitude of the velocity vector, which of course we abbreviate as lowercase v, just just scalar v, magnitude of the velocity. So what's going on the right-hand side, though? This is angle per unit time, not distance per unit time. So this is also something we can make sense out of, and you may or may not have seen this before. But if you're looking instead of distance per unit time, instead at angle per unit time, this is what we call angular speed. Again, I think that's pretty natural, right? Angle per unit time. Okay. All right, so with that set up, suppose I have not a single particle, but suppose I have a large mass. And could be two-dimensional, could be three-dimensional, doesn't really matter for what we're going to do here, but great big mass. And I ask, how much kinetic energy does this have as this great big mass is rotating around whatever that axis is? How would I compute the kinetic energy? Kinetic energy is a big deal, right? Very important. If you're interested in a motivation for this, here's one. Car wheels. Turns out when you drive a car, a non-trivial amount of the energy goes into making the wheels rotate. Right? It's not just getting the car itself to move, but the wheels themselves rotating. There's a lot of energy in there, right? So how do we compute how much energy? How does that amount of energy depend on the size of the wheel? Like if you've got the 22s, how does that compare to if you have like I don't know, what's the small ones, the 15 or whatever? How much difference does that make? Right. So this is a very real world, natural, important question to want to think about. Okay. All righty. Yeah, in this circumstance, a lot of people would say kinetic energy, 1/2 mv squared, high school physics. But you can't use that because different pieces of this mass are going different speeds, right? Again, so you got this great big mass here. A particle on that side, its speed is about like that. Over on this side, its speed is quite a bit more. So what is that speed? What is v if it's different for different parts of our mass? So this is not a well-defined thing. How do we deal with the problems that come up of if you have a region and you want to use a simple formula, but something's not constant? What do we do? Chop it up, add it up, right? This works for computing areas and masses and various other different things that we've talked about. So we're going to do a chop it up, add it up on that mass. What's the total kinetic energy of the whole? Hard problem. But if I look at all the individual pieces of mass, I can just add up all the individual little pieces of kinetic energy. And on a little piece, kinetic energy is 1/2 mv squared. Because on that little piece, there's a well-defined, that little teeny tiny little, chunk, that little grain or whatever particle of mass is, every part of it is going around at the same speed. So 1/2 mv squared straight out of there. And now a couple of little simplifying details. Let's not forget about the fact that speed, because we're talking about angular speed, is r times omega. Coming back up to our picture, while the big piece of mass, different pieces are moving at different linear speeds, the mass is rotating around cohesively, right? And so it's the same amount of degrees per unit time, same radians per unit. The rotation rate, the angular speed is the same for all the particles, even though the linear speeds are different. So that's the slick move here, is to realize that even though speed is not constant, omega is constant. And constants you can factor right on outside of the integral. Okay. Is everybody on board so far? And so you end up with this formula right here. So now this thing here, we're going to give that we're going to simplify that. We're just going to call it I for the moment, and we'll make sense out of why we care about that thing in a moment. But first thing I want to notice is our formula for kinetic energy looks an awful lot like our linear formula for kinetic energy. In both cases, it's 1/2 of something times a speed squared. Let's see here. So here it's linear speed squared. Here it's angular speed squared. Very, very similar formulas. And once you realize that, it's how about that? Son of a gun, if I can kind of pretend in some sense, I can recover this idea of kinetic energy is 1/2 of something times speed squared. If I just sort of interpret everything in this formula down here as being kind of an angular analog, an angular version of the things in the other formula. So in the same way that we think of that angular speed as being kind of, well, it's just an angular analog. I mean, look, regular speed is distance per unit time. This thing is angle per unit time. It's very naturally the angular analog of speed. Well, along those same lines, this thing, that integral, is the angular analog of mass, right? It's playing the role that mass did in the linear kinetic energy equation. So that thing is intrinsically interesting. It's the thing that makes everything fit together. It's the thing that plays the role that mass was playing when we compute kinetic energy in an angular context. And so we give it a name. It's an interesting thing. Interesting things should have names. That name is moment of inertia. And I got to admit, I don't know the etymology where they come up with this idea of moment. That seems weird to me. It's not like a instant in time sense of moment. It's just a different use of the word there. And I don't know what to tell you. Okay, so there's the physics. What I think is really interesting about this is, again, we're doing a chop it up, add it up. We were doing, though, what's weird about this, a chop it up, add it up argument on one physical quantity, namely kinetic energy. And what we got out of it was an interesting new concept that is not kinetic energy. What we got out of it is a new quantity to be interested in moment of inertia. So anyway, all right. So let's, oh, by the way, so you want to make sure to remember this formula, integral r squared dm. And we're going to do some examples. few minutes. Okay, integral r squared dm. Question then, what is r? Well, r, let's remind ourselves, is that distance. It's specifically, it's the distance from the axis of rotation to the particle that's rotating around it. So very importantly, this r, you cannot just assume that this is the polar coordinate r or the cylindrical coordinate r. It's very likely not. And randomly, sometimes, very conveniently, it might happen to be, right? But it's typically, generically, not the polar coordinate r. So, okay, well, if it's not the polar coordinate r, then what is it then? Well, it depends on your axis. So, for example, if you have a mass like that, that's rotating around that z-axis, well, in this case, it happens to be that, you know, looking at a piece of mass, rotating around the z-axis, that distance, you got to think about the geometry of the situation here, right? But that distance you can compute as that. So nice. But if you have a mass and it's rotating around a, you know, let's say some line parallel to the x-axis like that, you know, some line described by, you know, y and z are given fixed numbers. Then how do you compute this distance here? I think I messed up my colors, but oh well. How do you compute a distance from, you know, a generic point x, y, z to that line? Well, this is an interesting little geometry problem, and I'm going to, again, ask you all to fill in the details. This should be chapter 1 level computation, but that distance is that right there. Is that cool? Questions? All righty. Okay. Other examples. I mean, sometimes, you know, like if your axis is a coordinate axis, then sometimes it works out really nicely and conveniently. And in this case, because furthermore, the region that we're interested in here is entirely within the XY plane, then this distance, I guess, you know, if you wanted to be really careful in general about it, you could say it's the square root of x squared plus z squared, but z is always 0. And so that distance is just the absolute value of x. Okay. All right, et cetera. Okie dokie. So example. Now you'll notice the question asking as it does find the moment of inertia. The very first thing we write down is integral r squared dm. That's the generic formula for moment of inertia. Oh, yes.
So is it just a flat thing rotating?
Oh, in this example?
Yeah.
Yeah. Yeah, that's just like the one above. That's right. Yeah. So yeah, this is a two-dimensional. So points have 2 coordinates. So we're in 2 dimensions. That's right. And this describes in particular that, yeah, that flat region right there. Yeah. Okay. So moment of inertia means that's our formula. We just have to figure out the specs, you know, the details that go into this. Well, the domain we just talked about, the domain is that thing. What is R? R in this picture? Well, let's see. Oh, well, what am I rotating around? Well, I'm rotating around the x-axis. Here's the x-axis, and that means that my R is y. Everybody with me? Okay. And then let's see, don't forget your dm. Dm, of course, is density times dA, and density is given. Density is 2 plus cosine x. All right, so notice all I've done here is just plug into the generic formula. Generic formula is integral r squared dm. That's what you should memorize. I emphasize, don't try to memorize, please don't try to memorize the endless. Well, if you're rotating around this axis, then you get this formula. And if you're rotating around that axis, then you get that formula. Oh my gosh, right? It's going to go crazy. So just memorize integral r squared dm and then interpret accordingly. Interpret appropriately to whatever the circumstance is. Okay. All right, we are finally done with chapter 5. And moving on now to chapter 6. I suppose I'll interject here. None of what we're talking about today is fair game for the midterm exam. Right? Midterm exams on Friday. Hope everybody remembered. So this is all, stuff that'll be fair game for the third midterm exam, which again, like I said, for last month, not that far away, right? So we have to cover material today that's not fair game for exam 2, because we can't just take a day off. We don't have the time. And the remaining alternative would be to make today's material fair game for exam 2. Nobody wants that, right? So weird circumstance can't be avoided. But anyway, okay. So moving on to chapter 6. So we're going to talk about this new thing called a line integral. Line integral. And it's another kind of integral. It's another kind of chop it up, add it up. Now, y'all remember, we've talked about various different kinds of integrals. We've talked about single variable integrals, double integrals, and triple integrals. Really 3 kinds of integrals so far. They all have the common feature that they're chop it up, add it up. You're chopping up different things. You get different notions of size. Yeah. Different applications, of course, right? But in all 3 of the kind of integrals we've talked about so far, chop it up, add it up. Okay. Line integrals are the same in that sense. They're chop it up, add it up. It's just that instead of chopping up a 2-dimensional region inside of the plane, getting little pieces of area, or chopping up a 3-dimensional solid in space and getting little pieces of volume. Well, now we're going to chop up a 1-dimensional thing, a curve, perhaps in space, perhaps in the plane, whatever, sitting inside of, as I've got it drawn here anyway, a 2-dimensional plane. And it's tempting to say, well, we've done 1-dimensional integrals, we've done 2-dimensional integrals. Isn't this kind of one of the other? It seems like maybe it's one of the other of them. But it just isn't. It's just weird, right? It's tempting to say, again, well, we're in the plane, so this is probably a double integral, right? Can I just call this a double integral and start writing down double integral formulas? No, I can't, because if you take a curve and chop it up into little pieces, those pieces don't have areas, right? Or to just be more sort of blunt about it, if this, for example, was a a metal rod that had a known mass per unit length, right? It would be mass per unit length on a bent rod. It wouldn't be mass per unit area. So you can't use a double integral here. Single variable, Calc 1 level integral, of course, also obviously doesn't apply. In Calc 1, we never did an integral over a bent thing. We were always doing integrals on the x-axis, right? Okay. So this is a different thing. But again, chop it up, add it up. We're literally going to take, we're going to take our whole domain. We're going to chop it up into little pieces. Each little piece has a size on which I can talk about what I'm going to loosely call the density. And what kind of density is it? I don't know. It depends on your application. Maybe we're computing mass, in which case this is mass per unit length. Or maybe you're computing, maybe there's ants crawling on this thing, and I'm computing total number of ants. Then I'd be interested in ants per unit length, right? Whatever. But there's going to be quantity per unit length on that little piece, quantity per unit length that you'd want to multiply by length to get quantity. And of course, you then add up over the whole domain. Yes?
So is arc length a vector line?
Kind of. Now, we already wrote that down as as a an integral dt. We've already rewritten that as a single variable calc 1 integral, right? And technically, yes, the way that we did that is fairly similar to what we're going to do here. In fact, in my own book, I do those at the same time because they are fundamentally the same idea. But the book wants to treat that as a single variable integral, which by the way is fair game for the right, and to treat the more general version of it, where you have an integrand as being a different thing. So that's it. Yeah, it's just that's right. You're just you're just literally adding up the lengths. You're adding up a bunch of DS's. Yeah, exactly. So that's the point of view that it's different. And I point out that, okay, so the integrand is 1. So what? It's still, you're adding up. Anyway, don't get me started. Does that make sense? Yeah. Okay. Yeah. Okay. So chop it up, add it up. Now, of course, I know you look at this and it's tempting to say, you're just writing stuff down. We can't compute this. What in the world do I just take how do you take an antiderivative with respect to S, right? How to compute this, don't even be thinking about that for the moment, right? For the purposes of what we're doing here, forget about computations. This is just how to turn some application question into something that I can get down on the page so that I can represent an answer, and then we'll worry about how to compute it later, right? All this is saying here is, you chop up a metal rod into a bunch of little pieces, and the total mass is the sum of those little pieces of mass. That's all this is. Is everybody good so far? Okay, so so this is what we call a scalar line integral. Don't worry for the moment about why we call it a scalar line integral. But we call it a line integral because the domain is a curve, sometimes casually called a line. I wish this was called a curve integral, right? Because there is no implication here that this only works on geometric lines. Works on any kind of a curve. You do need it to be smooth in some sense. It can't be terribly nasty, but that's not our problem. Okay. All right, so this is called the line integral. Okay, how do we compute these things? Let's open up that question now. And I'll point out that this question has something in common with the change of variables circumstance. So flashing back to change of variables, what was our motivation to do change of variables? It was, I don't like this domain I've got. This domain's got corners all over the place. If I slice this up, I'm going to be hitting corners just everywhere. And the domain's bad. So what we did, the way we resolved the matter when you had change of variables was view that domain that you don't like as being an image of something. And then you do a pullback. And don't forget, when you do a pullback, you got to figure out what that stretching factor is, because images and things get stretched out when you make images. So strategically, we're going to do the exact same thing here. I'm going to take this circumstance. So specifically, I'm going to take this curve now, and I'm going to find a way to view it as an image of something. And then we're going to do a pullback and think about the stretching factor. Strategically, it's going to be just like we did with change of variables. So let's see the details. Turns out we've actually got most of this done already. We didn't even realize it. Because viewing a curve as being an image of something is called a parameterization. We already did it. We already know what these things are. We know loads of stuff about them, right? So we know how to parameterize curves. We know how to compute those little arc lengths, ds. They come, of course, from the velocity vector, right? So ds is, here it is, the size of the chunk ds is speed times dt. We're in business. Didn't even sort of realize it. Everybody with me? So yeah, so everything just kind of falls into place here. It's kind of beautiful. Yeah, here's our mysterious, creepy, I don't know what to do with this, abstract looking, okay, chop it up, add it up, but this line integral thing, I don't know what to do with it. No problem. ds is magnitude of velocity times dt. And you do the pullback, the new domain over here as well, from A to B on the t-axis. Off you go. This is very plug and chug, as it turns out. Is that cool? Yes.
Where did the f of x of t and dt come from?
Where did the well, I guess I didn't quite get to the f part, but that's the plugging in part. So f of stylus, f of x, right, is just a plug-in, but x is literally a function of t, and so I'm just rewriting x in terms of t per whatever the parameterization says. Yeah. Yep. Anybody else? A bunch of examples on the next page. I'm actually going to do 4 examples in parallel here. I'm going to compute a mass, both coordinates of a center of mass, and a moment of inertia. That's 4 examples. We're going to do this for a certain curve with a given parameterization and with a given density. So all of this is going to be as pertains to the exact same curve, right? And since all of the calculations concern the same curve, we're going to use, well, again, the same parameterization. It's going to have the same velocity, right? The same speed, namely the magnitude of velocity. All that's the same. So I like to do that part first. Get your stretching factor figured out, right? And with that done, it's just really very plug and chug. And here's how that goes. Let's see here. Starting off with mass. Well, mass accumulates. What's x bar? Oh, let's see here. Let me do this. What is x bar? You know what? Let me zoom out one spot. There we go. X bar is this formula. Y bar, analogous formula. Moment of inertia, integral r squared dm. This is all chop it up, added up stuff. I haven't really done any development yet, but those are just the basic formulas for those things. Then, of course, we've already talked about mass is density times size. That's the same in all of these examples. Let's see here. Then, get these to erase. There we go. Size is speed times dt from the previous page, right? So in all these examples, the same ds is vdt. And let's see, in all of these, we have the same actual speed. Right, everybody with me? So, some of the details are different on these, of course. So with the one on the left, I've got to deal with density. Well, density was given to be x plus y. That's in the statement of the question there. Density is x plus y. Well, in fact, that density is going to be in all of these. Let's go ahead and point that out. Density is x plus y. Wait a minute. How do I simplify x plus y? What are x and y? Don't forget, x and y are given in the parameterization. That's what the parameterization tells you, is how to rewrite x and y in terms of t. So specifically then, x is t. So that x is t. And likewise for all of them. And then furthermore, y is t squared in all of them. How we doing? Does everybody see how they're, I mean, so much of these integrals developments are exactly the same because they're on the exact same curve and they're all of the exact same density. And you know, the only difference is what happens in some sense at the very start of these integrals. And so, for example, you know, I've got an r squared over here. So yeah, I do have to figure out what r squared is. Well, we're rotating around the x-axis, it says. Around the x-axis, so r is y. And wait a minute, what is y? Well, y is t squared. Here, let me put it back in. There you go. So r is y and y is t squared. Yes.
So they all have the same stretching factor because they're all the same curve.
Yep, they're all four of these calculations are as pertains to the same curve, which I'm using the same parameterization. So yeah, same velocity, same stretching factor. Absolutely. Yep. Okay, so etc. So I like doing all these in parallel because I like pointing out how so much of the computation is curve dependent, not application dependent. And so I think that makes for a nice visual of that. And I'm bound to be out of time by now that I think about it. Yep, went a minute over again. Okay, good to see y'all. Good luck preparing for the test Friday. See you then. And yeah, good luck to everybody. Oh, and as usual, if you came in after I did the attendance, make sure to come up and let me know you're here.